For decades, the rhythmic thrum of the Ruhr Valley was the heartbeat of European economic stability. It was a sound built on the reliable, high-energy density flow of hydrocarbons. First coal, then a seamless transition to a massive network of pipelines carrying natural gas from the east. But today, that heartbeat is faltering. The furnaces that forge the steel for the world's most advanced machinery and the chemical reactors that birth global pharmaceutical giants are facing a physical reality they cannot ignore. The era of cheap, reliable gas is over. Germany is now standing at a precipice, forced to engineer its way out of a terminal industrial decline. The solution being proposed is not merely a change in fuel, but a total replumbing of the nation's industrial soul. Billions of euros are being diverted into what can only be described as the greatest industrial gamble of the 21st century, a transition to hydrogen. As we examine the blueprints of this massive pivot, we see a nation attempting to defy the laws of economic gravity. This investigation isn't about environmental idealism. It is about the cold, hard logic of survival. We are diving deep into the infrastructure, the physics, and the sheer capital required to sustain a superpower that has run out of its primary energy source. To understand how these systems operate and why their failure would trigger a global domino effect, you should join our community of thinkers. Subscribing to this channel and hitting the like button ensures you stay informed on the structural shifts that define our modern world, allowing us to continue providing this level of deep system analysis. By the end of this video, we will reveal the specific technical bottleneck that could render this entire multi-billion euro network obsolete before the first molecule even reaches the factory floor. The core of the German industrial crisis lies in a fundamental misunderstanding of energy. While the public focus is often on electricity and wind turbines, the backbone of heavy industry, steel, glass, and chemicals, cannot run on electrons alone. These sectors require process heat and chemical feedstocks that only a molecule can provide. Electricity, for all its versatility, cannot replace the reduction process in a blast furnace or provide the intense, consistent thermal energy needed to crack hydrocarbons into plastics. This is the molecule necessity. Germany's current infrastructure is a legacy system designed for methane, a molecule that provided high energy density at a low cost. To maintain its industrial supremacy, Germany must find a replacement that fits into its existing centralized logic. Hydrogen is the only candidate that fits the structural requirements of the Rhine-Ruhr complex. However, the transition from methane to hydrogen is not a simple swap. It requires a fundamental shift in how energy is captured, stored, and transported across a continent. We are witnessing the birth of a new energy framework, one that is being built out of necessity rather than choice, as the structural integrity of the German GDP depends entirely on the successful deployment of a hydrogen-based molecular economy. The German industrial miracle was never a product of mere policy or cultural ambition. It was a consequence of geological inevitability. To understand the hydrogen gamble of the 21st century, one must first look at the damp, coal-rich earth of the Ruhr Valley in the mid-1800s. Before the unification of Germany, the region was a collection of fragmented states, but beneath the surface lay the most concentrated energy source in Europe. It was here that the structural logic of the German state was forged. Figures like Alfred Krupp realized that industrial dominance was not about craftsmanship, but about the control of high-energy density thermal processes. The introduction of the puddling process and later the Bessemer converter required temperatures and chemical reduction capabilities that traditional fuels like wood could simply never provide. This created a systemic feedback loop that defined the nation for over a century. Coal powered the steam engines that pumped the mines, which provided more coal to the furnaces that forged the steel rails. These rails, in turn, allowed for the rapid transport of more coal and heavy machinery across the continent. By the time the German Empire was proclaimed in 1871, its power was physically manifested in the heat of the Ruhr's blast furnaces and the liquid conveyor belt of the Rhine River. This era established what we call the centralized industrial logic. It was a system built on the assumption that energy would always be concentrated, local, and abundant. The state's primary role was not to innovate, but to provide the heavy infrastructure, the canals, the railways, and later the pipelines, that allowed this thermal energy to reach the industrial heartland. When Germany transitioned from coal to oil and eventually to natural gas via the massive Ostpolitik energy deals of the 1970s, it wasn't changing its strategy, it was merely updating its fuel source while keeping the underlying plumbing the same. The reliance on cheap, piped molecules became the non-negotiable foundation of the German GDP. Today, as that foundation crumbles, the government is looking to hydrogen to serve the exact same structural purpose that coal served in 1850. They are attempting to recreate the coal-iron nexus without the coal, hoping that a new network of hydrogen pipes can provide the same thermal density and chemical reduction power that built the Krupp and Thyssen empires. It is a desperate attempt to maintain a 19th century industrial concentration in a 21st century world that is rapidly decentralizing. The current German crisis is not a temporary market fluctuation, it is a structural severance. For decades, the German industrial model, Modell Deutschland, functioned on a simple, albeit risky, arbitrage. Buy cheap energy from Russia, use high-precision engineering to transform it into premium goods, and export those goods to China and the United States. This model was physically anchored in locations like BASF's Ludwigshafen complex. Sprawling over 10 square kilometers, Ludwigshafen is the world's largest integrated chemical site, a city within a city that consumes more natural gas than some entire European nations. The site is a web of over 2,000 kilometers of pipelines designed to move methane and its derivatives with surgical precision. When a supply of cheap Russian gas was cut, these pipelines didn't just become empty, they became a terminal liability. The thermal energy required to run the steam crackers and the chemical feedstock required to produce ammonia and plastics simply cannot be replaced by wind or solar power. You cannot run a world-class chemical reactor on intermittent electricity without losing the scale and efficiency that makes the product competitive on the global stage. This is where the threat of deindustrialization becomes a physical reality. Without a cheap molecule to replace methane, companies like BASF and ThyssenKrupp face a choice: relocate their production to regions with cheaper energy, such as the United States or the Middle East, or watch their assets slowly rust into obsolescence. The German government understands that if these core industries leave, the entire economic ecosystem, the small to medium-sized enterprises known as the Mittelstand, will collapse along with them. This realization has triggered a frantic pivot toward hydrogen as a drop-in replacement. However, the thermodynamics of hydrogen are far less forgiving than those of methane. It is harder to compress, harder to transport, and significantly more expensive to produce. The gamble is that by subsidizing the initial transition, the state can keep these industrial clusters on German soil long enough for a global hydrogen market to mature. But as the cost of energy in Germany remains 3 to 4 times higher than in competing nations, the structural integrity of the entire nation is being tested. We are seeing the limits of engineering when it collides with the cold reality of global energy competition. To understand the sheer scale of Germany's ambition, one must look at the blueprint for the Wasserstoff-Kernnetz, or the hydrogen core network. This is not a gradual upgrade. It is a €20 billion surgical operation on the nation's industrial circulatory system. The plan involves a massive 9,700-kilometer network designed to link the windy northern coasts and southern industrial clusters with international import terminals. However, the engineering reality is far more complex than simply turning a valve. Approximately 60% of this network is intended to be repurposed from existing natural gas pipelines, a strategy designed to save time and reduce the astronomical capital expenditure of building entirely new infrastructure. But this repurposing brings a host of technical nightmares. Hydrogen is the smallest and lightest element in the periodic table, and its physical properties are notoriously difficult to manage within systems designed for the much larger methane molecule. The primary concern for German engineers is hydrogen embrittlement. In this process, tiny hydrogen atoms permeate the crystalline structure of the carbon steel used in traditional gas pipes, creating internal pressure and making the metal brittle over time. If left unmanaged, This leads to catastrophic structural failure and leaks that are nearly impossible to detect with conventional sensors. To mitigate this, every kilometer of the repurposed network must be meticulously inspected, coated with specialized polymer liners, or operated at significantly lower pressures, which in turn reduces the energy throughput of the entire system. Furthermore, the compressors required to move hydrogen are vastly different from those used for natural gas. Because hydrogen has such a low volumetric energy density, roughly 1/3 that of methane, you must compress it to much higher pressures or move it at much higher velocities to deliver the same amount of energy to a factory. This requires a total replacement of the existing compression stations with high-precision, multi-stage centrifugal compressors that are both expensive and energy-intensive to operate. The core network is essentially a bet that Germany can rebuild its 19th century centralized energy model using a gas that is physically predisposed to escape and destroy the very pipes meant to contain it. The state is effectively forcing an infrastructure lock-in, hoping that the sheer scale of the 9,700-kilometer network will create a network effect that drives down costs, even as the initial engineering hurdles threaten to balloon the budget far beyond the initial €20 billion estimate. It is an infrastructure play of the highest order, where the penalty for a single engineering oversight is the permanent deindustrialization of the Rhine-Ruhr heartland. The transition to hydrogen is not just a challenge of pipes and valves. It is a direct confrontation with the second law of thermodynamics. To produce green hydrogen, Germany is banking on electrolysis, the process of using electricity to split water into hydrogen and oxygen. The national strategy targets 10 gigawatts of domestic electrolysis capacity by 2030, but the energy math is sobering. Even with the most advanced proton exchange membrane or alkaline electrolyzers, the process is inherently inefficient. Approximately 30% of the electrical energy used is lost as waste heat during the initial conversion. This means that for every 100 units of wind or solar energy poured into the system, only 70 units emerge as hydrogen. When you add the energy required for compression, cooling, and transport, the total round-trip efficiency can drop below 50%. This creates a massive energy penalty that the German industrial base must somehow absorb. To replace the 95 to 130 terawatt-hours of hydrogen demand projected for 2030, Germany would need an astronomical increase in its renewable energy production, an increase that is currently far behind schedule. Furthermore, the physical density of hydrogen remains a primary bottleneck. To move large quantities of hydrogen across oceans from partners like Australia or Namibia, it must be liquefied. This requires cooling the gas to a staggering minus 253 degrees Celsius, a process that consumes another 30% of the energy contained within the hydrogen itself. The alternative is converting the hydrogen into ammonia for transport, which adds another layer of chemical processing, cost, and energy loss at both ends of the supply chain. Engineers are essentially fighting a war against physics to make hydrogen behave like the cheap, dense natural gas of the past. The scale of the equipment needed to handle these temperatures and pressures is unprecedented in civilian infrastructure. Large-scale electrolysis plants are not just simple machines. They are complex chemical refineries that require constant maintenance and a steady supply of ultra-pure water. If the water quality drops or the electricity supply fluctuates even slightly, the delicate membranes within the electrolyzers can be permanently damaged, leading to millions in lost capital. Germany's gamble rests on the hope that economies of scale will eventually overcome these thermodynamic realities, but physics does not grant discounts for volume. The energy-intensive nature of hydrogen production means that, unless electricity becomes practically free, green hydrogen will remain a premium fuel in a world where global competitors are still using much cheaper, albeit dirtier, energy sources. The sheer financial magnitude of Germany's hydrogen transition reveals a system that has moved beyond the logic of the free market and into the realm of state-managed survival. No private entity, regardless of its balance sheet, can independently shoulder the risks associated with building a continent-scale infrastructure for an unproven molecular market. Consequently, the German state has stepped in to become the ultimate guarantor of this transition, committing over €9 billion in initial federal subsidies and an additional €20 billion for the development of the core network itself. This is not merely a funding package. It is the creation of a massive financial shield designed to prevent a total industrial exodus. At the heart of this strategy is the H2 Global Auction Mechanism, a sophisticated double auction system funded with €3.5 billion. The mechanism acts as a middleman. It buys hydrogen from international producers at high market prices and sells it to domestic German industrial consumers at the lower prices they need to remain competitive. The state effectively pays the difference, subsidizing the green premium that would otherwise bankrupt a steel mill or a chemical plant. This creates a contract for difference model where the government absorbs the volatility of a nascent global market to ensure price stability for its industrial champions. However, this creates a dangerous systemic dependency. If the cost of producing green hydrogen does not drop as rapidly as projected, the German taxpayer could find themselves locked into a permanent subsidy loop, bankrolling the very energy that was supposed to provide economic independence. We are witnessing the birth of a subsidy black hole, where more and more capital is required just to maintain the status quo. If the state stops the flow of money, the infrastructure becomes a stranded asset, a multi-billion euro network of pipes and compressors with no one to use them. The government is essentially betting that the sheer volume of its subsidies will force a global market into existence through brute financial force. It is an attempt to use the state's balance sheet to override the fundamental cost disadvantages of hydrogen compared to traditional hydrocarbons. In this structural reality, the success of the German economy is no longer determined by the efficiency of its factories, but by the capacity of its treasury to sustain the highest energy subsidies in the industrial world. As Germany accepts that it cannot produce enough green hydrogen domestically to meet its industrial hunger, it is fundamentally rewriting its geopolitical playbook. The strategy acknowledges a sobering reality. Even if every available acre of German soil were covered in wind turbines and solar panels, the nation would still face a massive energy deficit. To bridge this gap, Germany must import between 50 and 70% of its hydrogen by 2030. This necessity is giving birth to what critics call a new energy colonization. The German government is frantically establishing hydrogen partnerships with nations in the global south, such as Namibia, Chile, and Australia, regions with vast, sun-drenched deserts and high wind speeds. The structural goal is to trade a dangerous dependency on Russian pipelines for a more diversified, yet equally complex, dependency on maritime, virtual pipelines. This shift requires the construction of massive export terminals in developing nations, often funded by German loans and built by German engineering firms. It is a system designed to export Germany's carbon neutrality requirements to the periphery of the global economy. However, the logistics of this new energy trade are fraught with systemic friction. Moving hydrogen across oceans requires specialized tankers that can maintain the cryogenic temperatures needed to keep the gas liquid, or the conversion of hydrogen into ammonia, which must then be cracked back into hydrogen upon arrival in ports like Rotterdam or Wilhelmshaven. Each step adds layers of cost, energy loss, and geopolitical risk. Germany is effectively attempting to build a global conveyor belt for a molecule that is notoriously difficult to move. This new dependency also creates a moral and political paradox. While Germany pursues a green future, it requires the massive appropriation of land and water resources in developing nations to produce the electricity needed for electrolysis. The structural integrity of the German industrial heartland now rests on the political stability of countries thousands of miles away. If a local government in Africa or South America decides to prioritize its own domestic energy needs or nationalize its hydrogen infrastructure, the German core network could find itself starved of the very molecules it was built to transport. The gamble is that by diversifying its suppliers, Germany can avoid this single point of failure trap it fell into with Russian gas. But in doing so, it is building a new form of energy imperialism, where the survival of the Rhine-Ruhr industrial complex depends on a global supply chain that is far more fragile and expensive than the pipelines of the past. The German hydrogen gamble is far more than just a pivot in energy policy. It is the final structural defense of an industrial system that has reached its thermodynamic limits. When we synthesize the complex layers of this transition, we see a friction that cannot be solved by sheer political will alone. On one side, we have the immense inertia of a 19th-century industrial complex, anchored in the physical geography of the Rhine-Ruhr, which requires a high-density molecular fuel to maintain its operational integrity. On the other, we have the harsh realities of hydrogen, a molecule that is notoriously inefficient to produce, expensive to move, and difficult to contain within traditional steel infrastructure. The construction of a 9,700-kilometer hydrogen core network represents the ultimate attempt to force these two opposing forces into alignment through brute engineering. This is an infrastructure-first strategy, operating on the assumption that if the pipes are built and the state provides the initial capital of 20 billion euros, a global market will inevitably follow. However, the energy penalty baked into this transition is systemic. By accepting a 30% loss during electrolysis and additional losses during the liquefaction or compression necessary for transport, Germany is effectively codifying a permanent cost disadvantage into its industrial exports. The state-led H2 Global Auction Mechanism acts as a vital financial bridge across this economic chasm, but it is a bridge built on the backs of taxpayers. If the global price of green hydrogen does not reach parity with historical natural gas prices, a goal that the laws of physics suggest is extraordinarily difficult without a massive technological breakthrough, the German industrial base will remain on permanent life support. This creates a precarious equilibrium where the nation's economic survival depends on the German treasury's capacity to subsidize every molecule flowing through the network. We are witnessing the transformation of the state into a utility provider of last resort, where the government must manage not just the infrastructure, but the very economic viability of its core industries. If this integration fails, the result will not be a sudden blackout, but a gradual rusting out of the German heartland as the high-precision sectors move to regions where energy is naturally abundant rather than subsidized. The hydrogen gamble is a race against time to prove that a centralized industrial superpower can survive in a world where energy has become decentralized and expensive. Ultimately, Germany is making the only move left on the board. The era of cheap, piped energy that fueled the post-war economic miracle has definitively ended, and there is no returning to that geopolitical status quo. The hydrogen push is a stark recognition that without a molecule-based energy carrier, the structural logic of the German economy, its chemical plants, its steel mills, and its vast supply chains, simply ceases to exist. It is a high-stakes play for global dominance that rests on the hope that German engineering excellence can overcome the brutal laws of physics and economics. Whether this gamble results in a triumphant rebirth of industrial supremacy or serves as the multi-billion euro epitaph of a once great economic power remains the defining question of this decade. But the systems we have explored today show us that this path was inevitable. Germany could not simply choose a different model without dismantling the very foundations of its society. As the first molecules of hydrogen begin to flow through the repurposed veins of the core network, the world will be watching to see if this audacious experiment can truly defy the odds. The success or failure of this transition will not just determine the future of the Rhine-Ruhr, but will set the template for every industrial nation facing an existential energy crunch. If you found this investigation into the structural realities of our world valuable, please consider subscribing to the channel and liking this video. Your support allows us to continue diving deep into the systems that govern our lives and uncovering the truth beneath the numbers. The narrative of industrial power is shifting, and we are here to document every technical and economic tremor along the way. Your engagement helps us maintain the investigative depth required to bring these complex stories to light. We will continue to monitor the progress of the hydrogen core network and its impact on global trade. Thank you for watching and for being part of this community of critical thinkers. See you in the next video.